Today we're going to be looking at related rates, which essentially just means two things that are happening at the same time, but not at the same rate, even though they are connected to each other. Before we start this though, it is important that you do the warm-up and make sure that you have a good understanding of some formulas. So make sure you've got this warm-up done first. Okay, if you have the warm-up done, then we're going to go forward. So related rate problems involve the rate of change for more than one quantity or variable. Most related rate problems will involve the chain rule to find the derivative. And we're going to often be finding the derivative with respect to time. And because we have more than one variable, we're going to be using our implicit differentiation strategy. So let's try an example that has no context. So here's the function. If 2x cubed minus y equals 5, and the derivative of y with respect to t, so with respect to time, is 3, I want to find the derivative of x with respect to time. And I want to know this when x is 2.5. So the first thing we're going to do is take the derivative of 2x cubed minus y equals 5 with respect to time. So I'm looking first at this first guy, and I'm going to take the derivative here. So I have my coefficient, I have my exponent, I have x to the power of 1 minus the exponent, and then I have the derivative of x with respect to time. Next, I'm going to take the derivative of minus y, which will be minus 1. And then I also have to say this is the derivative of y with respect to time. And all of that equals the derivative of a constant, which is 0. Now that I've had that done, I can plug in some values for the things that I know. So the derivative of x with respect to time is what I am looking to solve, but I do know this value, and that can go right there. And I do know the x value, and that's going to go right there. I'm going to write this all again, and I'm going to input the values given in the question. Okay, now that I only have one variable remaining, I can rearrange to solve. And I know that the derivative of x with respect to time is equal to 3, all divided by 2 times 3 times 2.5 squared. And when I put that into my calculator, I should get 0.008. Okay? So again, I take the derivative with respect to a certain variable. Often that variable will be time. And I plug in what I know, isolate and solve. All right, let's try a problem with a context. Two cars start at the same point and drive along perpendicular roads. Car A drives at a speed of 45 kilometers. Car B drives at a speed of 40 kilometers. Car B leaves 1 hour before car A. What rate are the cars separating 3 hours after car B leaves? So the first thing I'm going to do is I am going to draw a diagram. So I have car A, and I'm going to make car A go this way. And this is A. It's going 45 kilometers per hour. And then I'm going to say I've got car B. It's going perpendicular. There's B. It's going 40 kilometers per hour. All right, so now I have those two pieces of information. The next thing that I'm going to look at is that car B leaves 1 hour before car A. and I want to know uh, their rate of separation 3 hours after. So what I'm really looking for is this distance here. So the thing that I need to find out is actually how far away is car B 3 hours after? Well, if car B is going 40 kilometers an hour, if it travels for 3 hours, car B will have traveled 120 kilometers. Car A, on the other hand, leaves 1 hour after, and so it's only traveled for 2 hours, so it's only gone 90 kilometers. Okay, now I can set up my whole expression, and the relationship between these three variables is Pythagorean theorem. And I'm going to take the derivative of this with respect to time. Okay, so I'm going to take the derivative of A with respect to time, take the derivative of B with respect to time, and take the derivative of C with respect to time. Now that I've done that, I can start plugging in values. So this is the rate of A, which is 45 kilometers an hour, and the distance of A, which is 90 kilometers. This is the rate of car B, which is 40 kilometers an hour, and the distance that car B has traveled, which is 120. And what I don't know yet is this this rate. This is what I'm looking for, the rate that they are changing. I can, though, figure out this distance. And I can figure out this distance by using Pythagorean theorem before I take the derivative to see that the square root of 120 squared plus 90 squared is 150. So the distance, the actual distance, not the rate that they're separating, is 150 kilometers. And the rate of change, the rate of the change of C with respect to time is what I'm solving for. Now that I have everything all plugged in, I can see that I only actually have one unknown, the derivative of the rate, the distance between them with respect to time. And I can just calculate this out. And when I do that, I get 59 kilometers per hour. All right, let's try another one. All right, so water is pouring into an inverted right circular cone at a rate of 4 meters cubed per minute. The height and the diameter of the base of the cone are both 10 meters. How fast is the water level rising when the depth is 8 meters? So first, let's draw a picture. So I have a cone. It is 10 meters across. It is 10 meters tall. There is water that is being filled into this cone. Obviously, as the level of water gets higher, or as the cone gets more full, the rate at which it's filling is going to appear to decrease. The height, the depth of the water in the cone is going to decrease because it is the cone circumference is getting larger and larger as it's being filled. So I know that I've been given a rate here, and so I'm going to call that the rate that the volume is being changed with respect to time. And I also know this formula that the volume of a cone is pi r squared times height divided by 3. And if you don't know these, then you just need to look them up. Okay, so the first thing that I'm going to notice here is that I have too many variables. So what I'm going to do first, I'm going to think, what is the radius when the height is 8. Okay, so if I were to take a cross section of my full cone, so here I have 5 and here I have 10, I want to know what is this radius if the height is only 8? And if you look at this, you can see that this is actually a similar triangle. And we can actually see a relationship here that's going to be helpful. So if the height is only 8, then the radius is only 4. And the radius is actually always going to be 1/2 of the height because these triangles are similar. And that's helpful because now I have another way to write a variable which is going to reduce one of the unknowns. Okay, so that's what I'm going to do next. I'm going to reduce variables in the expression. Okay, so my original expression said volume equals pi r squared times h, divided by 3, but I don't want all of those different variables, and I want to actually replace radius with my expression in terms of h. So pi h over 2 squared times h over 3. Okay, I'm going to clean this up. So pi h squared over 4 times h over 3 is actually pi h cubed over 12. Now I have an expression with only one unknown. Okay, next, I'm just going to move over and get a bit more room. Now that I have that, I'm going to take the derivative with respect to time. So the derivative of the volume with respect to time is, take down the exponent, 3 pi h squared over my same constant as before, the derivative of h with respect to time. Okay, now that I have that, I can start subbing in my values where I know them. Okay, so I know the value of the rate of the volume changing. I know that's 4. That was given in the question. I still have 3 over 12 here. I can reduce it, but I can also just leave it as is. I know that the question is asking me for when the height is 8, so I'm going to put that in for my h value. And the rate of change of the height is what I'm actually solving for, so I do leave it as my one unknown. I'm going to rearrange to solve here the rate of change of the height with respect to time. Bring the 12 over, bring the 3 over, and bring the pi over and the 8 squared over. I'm going to end up with 1 over 4 pi meters per minute. Depending on the context of the question, you may leave this as a pi value, or you might potentially calculate it out specifically. Okay, there is one more question in this lesson. We're going to give it a try yourself first, and I'm going to post it in a different video.